Hello and welcome to Controllerstech. This is the 6th video in the STM32 Ethernet series using the W5500 module. In the previous video of this series, we covered how to create an HTTP WebServer on the STM32. Although the WebServer worked well, we still had one major limitation, which was the difficulty in transferring data dynamically. We created a few static pages and used buttons to navigate between them, but that approach wasn't ideal when we wanted live or changing data. Today, we will take the next step and learn how to send data to the web server and also receive data back from it. All this will be done using CGI, the Common Gateway Interface. CGI is a simple and effective method that allows a web server to run external programs and exchange information with them. When the browser sends a request, the CGI script processes it, and sends a suitable response back. It's an old technology, but it's still widely used in embedded systems because it is lightweight, easy to implement, and works very well for sending or receiving small amounts of data. In this project, I am going to control an LED connected to the STM32 using the buttons on the web page. There will also be a PWM slider on the page, and it will let us adjust the brightness of another LED directly from the browser. Finally, I am going to include a BME280 sensor to measure temperature, pressure, and humidity, and this data will be sent to the web page in real time. With all this, we will be able to properly test how our web server can transmit and receive data from the hardware. This project will be a continuation of the previous part, so the basic hardware connections will remain the same. The W5500 Ethernet module is connected through SPI, and a USB to UART converter is attached for logging and debugging. In addition to these basic connections, we will need a few more components and settings for this project. We will cover all of that in a moment, so let's start by opening STM32 Cube IDE first. As I mentioned, this is a continuation from the previous project, and here you can see part 5 already loaded into the IDE. Let's rename it to part 6, and make sure to check the update references box, so the project links remain correct. Alright, the renaming has been done. Here, the HTTP server folder is already included in the project, as we added it in the previous tutorial. Let's delete the HTTP server example files from the previous project, since we will use the newer version of them now. Now we will copy the new files required for this project, which contain the updated logic and the new CGI handlers. Let's take a look at the example source file. We have the two sockets assigned for the HTTP server, socket 0 and socket 1. There are three external functions declared for LED control, PWM adjustment, and reading the BME280 sensor data. There is also a single index page that holds all the buttons, sliders, and the sensor display area. We will open this page in a moment, but first let's walk through the functions that make everything work. The HTTP server setup function will first initialize the server and then register the system reset callback function. Since we have only one static web page in this project, we register it using the HTTP server web content. The HTTP server run function will then run the server on all configured sockets, ensuring that the requests coming from the browser are processed correctly. Other than these, I have added some new functions in this file. These functions handle the CGI get and post requests, which are essential for sending and receiving data dynamically. These CGI handler functions are already defined inside the HTTP utils.c file, but in their default state, they are empty placeholders. Once a CGI get request is generated by the web page, the HTTP get CGI handler function will be called. Inside this handler, the predefined get CGI processor is executed first. This is the reason we will place our custom code inside this function. Since we are writing the actual logic in another file, let's comment out the empty versions here to avoid confusion. The CGI GET request is sent by the sensor block on the web page to update the temperature, pressure, and humidity values. Therefore, we will first check if the request is coming from the URI sensor.cgi. If it is, we will call the function getBME to read the sensor values for temperature, pressure, and humidity. Then we prepare the buffer by formatting the data into JSON, which is how the web page expects to receive it. The buffer is part of the function's parameters, so we simply write into it. Finally, we calculate the length of the buffer, which is also passed back through the parameter. That is all we need to do here. The rest of the data handling will be taken care of by the W5500 library itself. Here we are getting an error because we are using floating point numbers inside sprintf. Let's fix this by opening the project properties. Then go to C++ build, settings, MCU/MPU settings. Here, enable the use float with printf option, and click apply to save the changes. Once this is done, the error should disappear. Let's see the setCGI function now. This function will handle the post requests sent from the web page. There are two CGIs on the web page that generate post requests. LED.CGI will control the LED, and PWM.CGI will control the PWM output. Here, we will first check if the request is made by LED.CGI. If it is, we will look at the data string sent by the web page. If this string is on, the LED control function will turn the LED on, and if the string is off, the function will turn it off. After adjusting the LED, we send the same data back to the web page, because the page uses this value to display the current LED status. You will understand this part much better once we examine the index page code. The PWM.CGI is handled in a very similar way. We extract the PWM value from the received data, and then call the PWM set function to apply the value to the timer channel. Here also we send a response back, even though the web page does not make use of it. Alright, let's see the index page now to understand everything clearly. At the beginning, we have some styling. These styles control the layout, the spacing, and the appearance of different elements on the page, so everything looks organized and easy to read. Then comes the LED control section. Here, we will have two buttons, LED on and LED off. When clicked, these buttons will call another function named setLED, and this function receives the string on or off, as its parameter. Other than the buttons, we also have a status indicator below to show the current state of the LED. This helps us easily confirm whether the LED is actually on or off after sending the request. The setLED function will call the fetch function to send a post request to LED.CGI and update the LED status on the server. The content type included in this request tells the server that the data being sent is formatted like regular HTML form data. The data will simply contain the string LED equals state, where the state value is either on or off, based on which button was clicked. That is why, in the post request handler on the STM32 side, we look for this exact data string inside the URI. After the string is found, we extract the LED state from it and process the request according to its value. After sending the request, the function will wait for the response sent by the server. Once the response arrives, it will update the status section with the received value. The server returns either on or off, so the same text is shown in the LED status indicator. Next, we have the PWM control section. This section contains a slider whose value can range from 0 to 255. When the slider is adjusted, it will call the function sendPWM and pass the current slider value as the function parameter. The function sendPWM will then call the fetch function to send a post request to PWM.CGI. The data part of this request includes the string PWM equals, followed by the PWM value. Inside the CGI handler, we look for the string PWM equals, and once it is found, we extract the value that comes after it. This function does not need a response because the web page does not show a PWM status, so there is nothing to update visually. Next, we have the sensor data section. This part of the page displays temperature, humidity, and pressure values from the BME280 sensor. To keep these values updated, I am calling a function named update sensors every 5 seconds. This function simply uses fetch to send a GET request to sensor.cgi. When the server responds, the function extracts the temperature, pressure, and humidity values from the JSON data received. These values are then updated in their respective locations on the web page. So that is all we have in the index page. Everything is handled using CGI, and there is no need to switch to a different web page. If you do want to load a different page, you can modify the CGI handler to send the full content of that page as the response. Enough of the explanation, let's make it work now. We need to configure the pins first, so let's open the CubeMX. The LED is connected to PC14, so set this pin as an output, as it will be controlled by our CGI request. Now we need to enable I2C for the BME280 sensor, and I am going to use I2C1 for this project. Leave everything at the default settings in the I2C configuration, since the standard setup works perfectly for the sensor. Next, we need to enable the PWM output. For this, I am going to use timer 2, channel 2. Here, the pin PA1 is configured as the PWM output pin, so let's set up its parameters now. The PWM slider on the web page can vary between 0 and 255, so we will configure the auto reload value to match this range. This makes it easier to map the slider value directly to the duty cycle, allowing smooth brightness control for the LED. Let's set the prescaler to 100, which will reduce the PWM frequency to a more suitable level for visible LED dimming. If you want detailed information about how PWM works or how these values affect the output, you can check out the video linked in the top right corner. That is all we need to configure in CubeMX, so click Save to generate the updated project. Let's take a look at the additional connection diagram now. The BME280 sensor is connected via I2C on pins PB6 and PB7. It is powered directly with 3.3 volts from the STM32 board itself, as the sensor requires a stable, low-voltage supply. There are two LEDs connected to PC14 and PA1. The first LED is used for simple on-off control, while the second LED is used for PWM output. Make sure to connect a 200 ohm resistor in series with each LED to limit the current and protect the pins. Alright, let's see how to implement the server now. Include the HTTP server example.h file inside the main file. This header provides the external functions and structures we need for handling CGI requests and overall server control. I have downloaded the BME280 files from my earlier tutorial, so let's copy them into the project as well. After adding the files, include the BME280 header in the main file so we can access the sensor functions. The LED control function is already implemented in the main file, but we need to add a few more functions here. There are two additional external functions defined in the HTTP server example file, so let's start by writing the PWM set function. Inside this function, we will simply pass the received value to the CCR2 register of timer 2. This directly updates the PWM duty cycle and controls the brightness of the LED connected to the PWM pin. Let's write the getBME function now. I have already covered the BME280 setup in a separate tutorial, so we will copy the initialization code from there. Let's take this configuration function and paste it into our project, placing it before the W5500 module is initialized so everything starts in the correct order. Next, to read the sensor data, we need to call the function BME280 measure. So let's call it inside the getBME function. This is everything we need for retrieving temperature, humidity, and pressure values from the BME280. We also need to start timer 2 in PWM mode, so let's enable it inside the main function before entering the while loop. Alright, let's build the project now. We have a few errors to resolve. The first error is related to HTTP dynamic handler. We defined this function in the previous video, but it is no longer used in this project. So we need to remove it from the http server.c file. Let's delete the function, and build the project again. We still have an error, and this time it is due to flash overflow. The blue pill does not have enough flash memory to hold the entire project with the BME280 code included. Just to test the server, I am going to exclude the BME280 related functions from the project for now. As you can see, the code builds correctly, and the flash usage is almost at its limit. Instead of reading the actual temperature and other values from the BME280, I am going to use a simple count variable to generate some dummy data. This will allow us to test the CGI communication without the actual sensor library. There is one last step remaining. Inside the LED control function, we will use the PC14 pin to toggle the LED. That's it. Let's build and flash the project to the board. Finally, open the serial monitor to view the logs. The server is up and running. This is the server's IP, and as you can see here, the server is operating with 2 ports assigned for HTTP communication. Let's open the browser and enter the server's IP address. Here, you can see that the index page has been loaded successfully. We have separate sections for LED control, PWM control, and sensor data. The sensor data is updating every 5 seconds. You can also see the requests appearing in the serial logs. Here, a GET request is generated by the browser for sensor.cgi, confirming that the page is requesting fresh data from the server at regular intervals. Let's continue with the browser now. When the LED on button is clicked, the LED turns on. Also notice that the status indicator updates to show on. Similarly, clicking the LED off button will turn the LED off, and the status changes to off. Let's test the PWM slider now. You can see that the LED brightness changes based on the slider value, which means the PWM control is working correctly. The LED control and PWM control both use post requests, while the sensor section uses GET requests to retrieve data from the server. Both request types are functioning well, which means our server is now able to handle dynamic communication in both directions. We now have a complete web server that can handle static content and dynamic data exchange using CGI. This wraps up the HTTP server part of this series. In the next video, we will implement an MQTT client on the STM32 using the W5500 module, which will take our network communication to the next level. That is it for this video. You can download the full project from the link provided in the description. Leave a comment if you have any questions or doubts. Keep watching, and have a nice day ahead.